And we're back for what I hope to be the exciting conclusion to section 7.3. We're going to do another problem just like we did on the bottom of the previous page, but let's take a look at him. So we've got x1 prime equals negative x1 plus 3x2, and x2 prime equals negative 6x1 plus 5x2. Again, we have a system of first order linear differential equations, and we can create a matrix with those coefficient functions, which happen to be constants here. And our constants are -1, 3, -6, and 5. And so let's try the eigenvalue method for solving this. So once again, to find eigenvalues, we need ax equals lambda x, which after a couple of baby algebra steps is a minus lambda I x equals the 0 vector. But to find the eigenvalues that work, so we can then find the eigenvectors, we need to find the non-trivial solutions to this. So we need the a minus lambda I matrix. So that would be -1 minus lambda, 3, -6, and 5 minus lambda. We need to take that and set that equal to 0 to get our characteristic equation. And when we do that, we get -1 minus lambda times 5 minus lambda minus 3 times -6, which is -18, equals 0. And let's see what we got. So we've got lambda squared. We get a plus a lambda minus 5 lambda is minus 4 lambda, and then minus 5, and then plus 18. Okay. And let's see. So that gives us lambda squared minus 4 lambda plus 13 equals 0. I'm going to go ahead and just write that as, I'm going to write the minus 13 on this side, and it looks like I'll probably want to do some completing the square. Well, let me not skip that step. So lambda squared minus 4 lambda plus 13 equals 0. So I couldn't find a nice thing that would factor on this, so it probably isn't going to factor over the real numbers. So let's try completing the square. Half of the linear term squared would be add 4. And if we add 4 to that side, we need to add 4 to this side. Getting lambda minus 2 quantity squared equals -9. Okay. And if we take the square root of that, we're going to get lambda minus 2 is equal to plus or minus square root of -9, which is plus or minus 3i. And finally, we get lambda equals 2 plus or minus 3i. So our solutions are going to deal with these guys. Let's go ahead and just take the 2 plus 3i guy. So lambda equals 2 plus 3i. Now let me move this up so we've got a little bit more space here to work. We can still do this. It's going to be a little bit harder, but we can still do it. So a minus lambda I times x is equal to 0 vector is what we're trying to solve again. But now lambda is a complex number. So we're going to have -1 minus 2 plus 3i. -1 minus 2 plus 3i. 3, -6, and 5 minus lambda, which was 2 plus 3i. And remember that we're solving the system where this is equal to 0. Okay. So let's do some work on that. -1 minus 2 is -3 minus 3i when we distribute the negative sign. 3, -6, and 5 minus 2 is 3 minus 3i is 0, 0. And let's go ahead and see if we can do a little bit of work here with some row operations. Okay. The first thing I'm going to do is I'm going to times by, how about -1/3 row 1 replacing row 1. If I do that, I'm going to get 1 plus I, -1, 0. And we still have -6, 3 minus 3I. Okay. Oh, let's not forget my 0 here. And then when we've been playing with the 2x2 matrices, we noticed that the second row was always a row of zeros. It's a little harder to see what I'd need to multiply by here to kill this -6, but what if I were to multiply this by 3 minus 3I and then add it to that? So let's see what happens when we do 3 minus 3I times row 1 added to row 2 replacing row 2. Now row 1 still stayed the same as 1 plus I and -1 and 0, of course. And this is going to have to be a 0 as well. But let's see what happens when we do, let me do my scratch work over here. 3 minus 3I times 1 plus I. So we're going to get 3 plus 3I minus 3I, which makes 0. Let me write that out, plus 3I minus 3I. And then minus 3I squared, which is plus 3. And so we will get 6 for this guy right here. Oh, and the 6 plus the -6 makes 0. And when I do the -1 times the 3 minus 3I, we get -3 plus 3, which is 0, and plus 3I minus 3I, which is 0. Okay. Now what we're going to do here, normally we put this into completely reduced row echelon form, but this book likes to stop here and say, well, let's let A be 1 and B be whatever he is. So if A is 1, we've got 1 plus I minus B equals 0. Adding B to both sides, we then see that B is 1 plus I. And so our eigenvector corresponding to this eigenvalue is 1, 1 plus I. Looks like we are going to need another video. So let me stop so we keep this under 10 minutes.